Today we can discuss the units of rate constant of order of reactions. Unit of rate constants of reactions of different order. We can represent a reaction as A gives product. A is reactant. Reactant gives product. The rate law can be represented as rate is equal to K into concentration A raised to N. N represent order of the reaction. We can rearrange this equation as K is equal to rate divided by concentration of A raised to N. You know the unit of rate. What is the unit of rate? Change in concentration per time taken for the change. That means mole per liter concentration. Second time. So mole per liter per second. That is the unit of rate. What is the unit of concentration? Mole per liter. So what is the unit of rate constant? K. Mole per liter per second, or mole liter raised to minus 1, second raised to minus 1 divided by mole per liter raised to N. N is the order of the reaction. So for an nth order reaction, the unit of rate constant can be represented as mole raised to 1 minus N, L raised to N minus 1, and second raised to minus 1. So for a zero order reaction, N is equal to 0. So mole raised to 1 minus 0, 1. L raised to 0 minus 1, minus 1. Second raised to minus 1. So what will be the unit? Mole liter raised to minus 1, second raised to minus 1. For a first order reaction, N is equal to 1. Mole raised to 1 minus 1, 0. L raised to 1 minus 1, 0. Second raised to minus 1. So what is the unit? Second raised to minus 1. That is the unit of first order reaction. Second order reaction, N is equal to 2. Mole raised to 1 minus 2. That is minus 1. L raised to 2 minus 1. 1. Second raised to minus 1. So what is the unit? Mole raised to minus 1, liter, second raised to minus 1. And from the unit, we can find out the order of the reaction. For example, here you can see a question. Identify the reaction order from each of the following rate constants. K is equal to 2.3 into 10 raised to minus 5 liter, mole raised to minus 1, second raised to minus 1. So what is the unit of rate constant? Liter, mole raised to minus 1, second raised to minus 1. Here you look, liter, mole raised to minus 1, liter, mole raised to minus 1, second raised to minus 1. So what is the order of the reaction? It is a second order reaction. Now K is equal to 3 into 10 raised to minus 4 per second. Per second is the unit of rate constant of a first order reaction. Per second, the unit of rate constant. So from this, it is very clear. If you know the unit, you can identify the reaction is first order, second order, third order, or zero order, or half order. Whatever it may, we can identify it very easily. And now we can see some of the examples or reactions of different orders. All photochemical reactions and decomposition of gaseous molecules such as NH3 on metal surface are examples of zero order reactions. Photochemical reactions are very fast reactions. We cannot say the rate of the reaction is depending on the concentration of the reactant. That is independent of concentration of the reactant. Therefore, that is a zero order reaction. So all photochemical reactions, zero order reactions. Decomposition of gas on metals are for zero order reaction. Now first order reaction, example, radioactive reactions are first order reaction. Reactions in which alpha, beta, gamma radiations are emitted. Examples are first order reactions. Another example, NH4NO2 gives N2 plus 2H2O. It is a first order reaction. 2N2O5 gives 4NO2 plus O2. It is another first order reaction. Now second order reaction, 2HI gives H2 plus I2. This is an example for second order reaction. 2NO plus O2 gives 2NO2. An example for third order reaction. H2 plus Br2 gives 2HBr. An example for 1.5 order reaction. So these are some of the examples of reactions of different orders. We can see what is molecularity of a reaction. Already we discussed the order of reaction. Order of reaction is an experimental quantity, but molecularity of a reaction, a theoretical quantity. Molecularity of a reaction can be defined as the number of molecules which collide simultaneously to bring about the chemical reaction. But there is a problem in complex reactions. We cannot imagine the collision of a simultaneous collision of 10 molecules. So such a reactions, molecularity is meaningless, cannot be applied in such reactions. So in the case of simple reactions, or in the case of elementary reaction, the molecularity of reaction is defined as the number of molecules which collide simultaneously to bring about a chemical reaction. So theoretically, molecularity is equal to the sum of the stoichiometric coefficients in the balanced chemical equation. An example is given here. 2Hi gives H2 plus I2. What is the molecularity? 2. This is the stoichiometric coefficient of the reactant. In order to understand clearly what is molecularity and what is order of a reaction and what is the relationship between order and molecularity, we have to study the mechanism of the reaction. What is meant by mechanism of a reaction? It is the sequence of elementary reactions which leads to the complete reaction or to the overall reaction. That is mechanism of a reaction. Last year you have studied it in the organic chemistry, reaction mechanism. So if we analyze a chemical reaction, sometimes it may take place in different steps. And in that step, one will be a slow step and others will be fast steps. Here we have an example, decomposition of hydrogen peroxide. It will take place in 2 steps. And in the first step, H2O2 react with I minus to give H2O and IO minus. IO minus. And this IO minus is highly unstable, and therefore this IO minus will react with H2O2 to form H2O, I minus, and O2. H2O, I minus, and O2. When you add the reaction first and second, you get the total reaction. What is the total reaction? H2O2 plus H2O, 2H2O2. 2H2O2 plus I minus is present in the reactant side and I minus is present in the product side. It is reactant side and in the product side. So it will cancel each other. IO minus present in the product side and also in the react side. That will cancel each other. So what is remaining? 2H2O2 gives 2H2O plus O2. 2H2O2 gives 2H2O plus O2. And here, the second step, there is an unstable IO minus. Therefore, that will be a fast reaction. But in the first step, H2O2 is stable and I minus in aqueous solution, that also stable. H2O2 is stable and I minus also stable. Therefore, the first step will take place slowly. That will be a slow reaction. And that slow reaction is the right determining step. For example, in our school, we are conducting cross country. In cross country, there are 6 participants. If all the 5 are running very fast and the 5th one is very slow, the position of the team will be decided by that slowest person, isn't it? You know it. Similarly, in a chemical reaction, the slowest step determines the speed or the rate of the chemical reaction. So if slowest step determines the rate of the reaction, we can say molecularity of the slow step is the order of the reaction. Molecularity of the slow step is the order of the reaction. Now you will get the idea about what is molecularity and what is order. So order you will get it from an experiment, only from an experiment, or when you analyze the mechanism you will get order. So here the slow step is first step. So what will be the right equation or right expression? Right is equal to K into concentration of H2O2 into concentration of I minus. So we can say it is a second order reaction, 1 plus 1, 2, second order reaction. That will be the right expression. You can say right is equal to K into concentration of H2O2 into concentration of I minus. So here we can compare order and molecularity, the properties or characteristic of order that we discussed earlier, and molecularity, some of the properties we discussed here. Now we can compare it. Sum of the powers of concentration terms in the right law is known as order of reaction. And what is molecularity? Number of molecules which collide simultaneously to bring about the chemical reaction. An order of reaction is an experimental quantity, but molecularity is not an experimental quantity that can be determined from balanced chemical equation. So we can say molecularity is a theoretical quantity. In the case of order, it can be zero, fractional values, or integral values, whole numbers. But molecularity cannot be zero. Molecularity cannot be fractional numbers. Molecularity always integral numbers. Order is applicable to elementary as well as complex reactions. But molecularity already we mentioned. For complex reactions, it is meaningless, not applicable. So these are the some of the comparisons between order and molecularity. I think we can stop it today, and next class we can see the integral right equation.